Nice to see you after the weekend. Everyone back. It's good. So, short recall of our previous lecture. We distinguish between scalar and vector quantities in physics. As an example, we considered some path and displacement. So path is technically the length of the trajectory, how along which the object was moving from point A to point B. And obviously it takes information about trajectory, but represented just with a number. At the contrary, we have also displacement as a vector which connects initial point and final point of the trajectory, point A and point B. And that is displacement vector, which defines not only the distance between 2 points, but also their orientation with respect to each other. So it defines the direction in addition to the magnitude. We obviously need to do some operations with vectors. So we considered how it's possible to add vectors, subtract vectors, to multiply vectors by scalar number. Also how to multiply vector by another vector. And there were two options. One is dot product and another is cross product. So if we consider dot product, it's what gives us eventually a scalar. So dot product of two vectors gives us a scalar. That's something like force and displacement. Both vectors we have work and as a scalar quantity. And cross product gives us another vector. So, but this vector is always perpendicular to the vectors which are multiplied via cross product, and its direction is defined by a right-hand rule. So we also derive the equation how it is possible to multiply two vectors in this cross product. And please refresh this information because quite soon will be necessary to deal with vectors very often. So today we make first step into mechanics, and we open this topic with kinematics, this subsection of mechanics, which tries to understand where body will be located in a given moment of time. So we have either one or multi-dimensional space. So let's say 1, 2, or 3-dimensional space, and with some given parameters at the initial condition when time is equal to 0. We want from this given starting point, we want to know at each moment of time where this body will be located. So kinematics doesn't answer any questions related to the reason of motion, that is dynamics, and that we will discuss in the future. Now, we only want to have full information about position as a function of time. And in other words, it's so-called kinematic equation, which can provide us all this information. So we start from motion along a straight line, and then we will, maybe in the next lecture, we will go already to dimensional case. In the case of motion along a straight line, we don't deal with vectors because it's not necessary. We have only one axis, and direction can be given in a different form than vector. So let us discuss this in more details. So we consider some axis x, and here is our body. Let's say its initial position at x equals 0. Since we have motion along straight line, we cannot move this body up and down or closer to us or further from us. So it moves only left and right in this configuration. So it means that we can move it either to the right along axis x or to the left in the opposite direction. Let's say it moved to the right and its new position is defined by some coordinate x1, and if we move it to the left, here is x2. So now how we define the direction of motion? Since we don't have a vector here, we don't operate with vectors, we can just consider that direction of this axis x is positive direction. Then if we have displacement along axis x, this x1 will be positive, and in the opposite case, x2 will be negative. So we define only by the sign of displacement, and that will give us the direction of motion. So we can write that x1 is positive and x2 is negative. So obviously, if we start not from 0, let's say we have some case when we start from some coordinate x1, this is our body here, at initial moment of time, then it moved to the right, for instance, occupied new position at coordinate x2. So displacement we will determine as difference between x2, like coordinate of the final position, minus coordinate of the initial position. So x2 minus x1. And in this case, it will be positive because it's moving along positive direction of axis x. So now we still consider motion along axis x, along straight line, but as a function of time. So we want to plot, to have some plot and show how position along axis x changes with time. So let us show it here. It will be position x along this axis x, and here is time. So we, let's say, have such a dependence. So what does it mean when x is increasing over time? Any suggestions? Yeah, where does it in terms of motion along axis x? Yeah, so if x increases, then we know that this object is moving to the right along axis x. Then when it decreases, obviously it starts to move back. So it goes back and forth. It still moves in the one direction. So this is our axis x, and it's this time. So don't confuse with motion in two-dimensional space when we have x and y coordinates. So now when we have this, let us consider some points here, like two moments of time. It will be defined by t1 and t2. So obviously for each of these moments of time, we will have some corresponding value of position x. So we can look here and here. So this will be x1 and this is x2. So now let us introduce one of the important parameters for kinematic equation. And maybe before we do that, let us discuss what actually we need to know in order to be sure that at every moment of time we can determine position of this body. So which parameters we need to know? Huh? Velocity, that's correct. Yes. What else? Acceleration. Now, well, time we know is kind of independent parameter. It flows independently. Okay, initial conditions. So we need to know where this body is located at the beginning, at t equals 0. We need to know initial values of velocity and acceleration. So this is clear. Now let us discuss a little bit about velocity and accelerations, which you mentioned. So there are generally considered two types of velocity and accelerations. We can talk about average and instantaneous. So average means we get some average value of velocity in some time interval. And instantaneous, we get the value of velocity at a given moment of time. So in order to get finally this kinematic equation, we need to know information about instantaneous acceleration and velocity. It means that we need to know velocity and acceleration as functions of time. So in every moment of time, we need to know their values. And that is different from average values. So now let us first introduce the average velocity. So V average will be equal, if we look at this plot, here we have delta x, here we have delta t. So we can write that average velocity will be equal to x2 minus x1 divided by t2 minus t1, or delta x divided by delta t. So this is the definition of average velocity. Average means that you will get some information of velocity of this body in the interval defined by this time t1 and t2. So that is definitely not enough, and we need to make one additional step in order to get the instantaneous. So how it works? We go for limit. We go for limit when delta t change in time, this time interval between these 2 points, approaches to 0. What does it mean? Because we pick up this point t2 and move it to t1 so close that it stays in the vicinity of t1. So the difference between t2 and t1 becomes approaching to 0. Obviously, the same will happen with x2 and x1. When we move t1 approaching to, sorry, t2 approaching to t1, this will happen with x2 approaching to x1. So that is the definition of limit. And in this case, we can apply first derivative of position over time. So let us write how it looks like. So instantaneous value of velocity will be defined as limit of delta t approaching 0, delta x divided by delta t. So in this case, it will be dx over dt, and that is first derivative of position over time. It's still average value, but since we make this interval so small, it will be average value in the vicinity of point t1. So we can claim that the value of velocity, which we get by taking first derivative of position versus time, will give us the instantaneous value for this velocity in this given moment of time t1. So now the second parameter which we mentioned is acceleration. And if velocity is change, like speed, like change of position, how fast position is changing over time. Then acceleration is defined how fast velocity is changing over time. So we can write that average acceleration is equal to v2 minus v1 divided by t2 minus t1, or delta v over delta t. Again, it's not enough for us. We want to know instantaneous values, and that's why we get instantaneous value as a limit of delta t approaching to 0, delta v divided by delta t. That is first derivative of velocity over time, dv over dt, or it can be represented as a second derivative of position over time, d square x over dt square. So now we define two parameters which are critical to be known for derivation of any kinematic equation. Let us try to apply this knowledge already, this definition, in deriving kinematic equation for an object which moves along a straight line with a constant acceleration. So that will be our goal. Let us show such a system. We have axis x, then we have our object, which starts at moment of time t equals 0, some coordinate x naught. So that's initial position of this body defined on axis x. At this time t equals 0, velocity of this object, let's say it's also oriented along both velocity and acceleration, oriented in the positive direction of axis x, is v naught. And acceleration a is constant. So what will be the difference between average and instantaneous values of acceleration? The same, because it's constant. So we don't distinguish when we have some constant parameter, we don't distinguish between average and instantaneous. It remains constant at any moment of time. So we already know that in every moment of time, it is a just acceleration given value. Okay, with this, we can consider here that acceleration, instantaneous acceleration, is equal to first derivative of velocity over time. Now we can rearrange it, and it will be dv equals to a times dt. So when we want to go from small change of parameter to determine its value, we need to integrate. I'm not sure how it was introduced in your school, this concept of calculus, like basics of calculus, means derivation and integration, but very basic knowledge of derivatives and understanding of derivatives and integrals, that is definitely needed. So please double check that you have this very basic understanding. We don't solve here any difficult integrals, but you just need to understand what it is. So it's the opposite process of taking a derivative. We can come back to original function, and in order to do that, we need to integrate. So now how we get the value of instantaneous velocity. V will be, bless you, V will be equal to integral of a times dt. Since a, we know it's a constant, we can take it out from the integral because it allows us. So a is a constant. Here we have times integral of dt. So integral of dt just gives us t is time. So it will be a times t. And taking into account that we have to deal now with not defined integral, we have also one constant. So we get this analytical solution with some constant, which we need to determine, C1 constant. So now the question is how we determine this constant, because we cannot stop at this point. We need to have the final equation, which describes our specific case. And this constant should be defined. Any suggestions? Yeah.
Time is equal to 0 and the initial. So we say that the initial velocity with the time of 0 will be C1.
Okay, so this what you are describing is called that we apply boundary conditions. So boundary conditions in our case will be the initial condition. And you are right, in initial condition, we know what will be the velocity at t equals 0. So let us take this into account. At t equals 0, v, instantaneous velocity, will be equal to v naught. Now we can substitute these values into our equation. So we will have v naught, instead of v we put v naught. That is equal to a times 0, because time is equal to 0 at initial point, plus c1. So this guy will be equal to 0. And from here we can write that c1 is equal to v naught. So with this we can write the equation, which will give us velocity, instantaneous velocity, plus u as a function of time. So velocity as a function of time is given to v naught plus a times t. So now we have this step done. We know how which function describes velocity as a function of time. And obviously we need to take this information to make one more time in order to get information further about position as a function of time. Because keep in mind, kinematics wants to answer this question. We want to get position as a function of time. So we can write here, as recall from definition of the acceleration, or definition of the, so we consider definition of acceleration here. Now we consider definition of velocity. So we can write that v is equal to dx over dt. So from here again, we write that dx is equal to v times dt. And from here, we get position of the body as integral of v times dt. So v is a function of time. So instead of this v, we need to substitute its expression, which we have just derived. So that's why we will get the following. It will be integral of v naught plus a times t times dt. So if we have integral of a sum, that means we have sum of integrals, so we can split this integral in two components. So that will be integral of v naught times dt plus integral of at times dt. So in this first integral, it will be v naught. We can take out these constants because v naught and a, they are constants. So it will be v naught times dt, integral dt, plus a times integral at, oh, sorry, not a, we took it out already, it will be t dt. So first integral will give us v naught times t, so this one, and the second will be plus a times t squared divided by 2. And obviously, since we have not defined integral, we will have some constant c2. I would like to draw your attention to this term, at squared divided by 2. As you remember, during our dimensional analysis lecture, we tried with help of dimensional analysis to estimate how position will depend on time if we have constant acceleration. So we got numerator of this term, so it was a times t squared. So we got it with accuracy of some constant 1/2. But here now we get the analytical solution, so it's the correct one. So now we have again this constant c2. We need to apply boundary condition, but in this case a bit different. We know that at t equals to 0, x is equal to x naught. So taking this into account, we can write that x naught is equal to v naught times 0 plus a times 0 square divided by 2 and plus c2. From here, since these guys are equal to 0, we have c2 equals to x naught. X naught. So now we actually have the full information to write the kinematic equation for this particular case when we deal with an object which is moving along a straight line with constant acceleration. So the final expression for position as a function of time will be equal to x naught plus v naught times t plus a t squared divided by 2. So this is the kinematic equation and means that with the help of this equation, we can define position of the object at any moment of time, considering, of course, initial position and velocity, and also the fact that it moves with constant acceleration, a. So we have kind of three terms which define the final position of the object at given time. So it will be initial position, the displacement originated because of initial velocity, and displacement originated because of acceleration, constant acceleration of this object. At this point, we can do some manipulations here in order to express kinematic equation in a bit different form. So we don't deal with time anymore, and we can express velocity as a function of position. Sometimes it really depends on given parameters and conditions in problems you need to solve. It happens that it's easier and better to use kinematic equation in a different form. So in order to do that, let us write here next to this kinematic equation also equation which we derived for instantaneous velocity. So we can write here V is equal to V naught plus A times T. From this equation, we can express time and substitute it into our kinematic equation. So from here, we get time equals to V minus V naught divided by A. And now we substitute it into our kinematic equation. So x, I don't write here x as a function of time. We already remember this. So it will be x naught plus V naught times V minus V naught divided by, by A. Then we have plus A times V minus V naught divided by A square, and this is divided by 2. So what we have here, let us, well, here we have A square in the denominator and A here, so we can cancel this A. So it will be, we can write here next x equal to x naught plus V naught V minus V naught minus plus V minus V naught square divided by 2A. Okay. We lost A here, yes? Yes. Okay, yeah, you are right. Thank you. So now let us multiply this by 2A and move this x naught in the left side of the equation. So it will be x minus x naught times 2A here, because we multiply both left and right sides. So here will be 2 times V naught times V minus V naught. And here we have just plus V minus V naught square. So if we have this V minus V naught square, so just as recall, if we have A minus B square, that should be A square minus 2 times AB plus B square. So now we need to do it with V and V naught. This will be equal. Now we open this parenthesis. It will be 2V naught times V minus 2V naught square plus V square minus 2V times V naught and plus V naught square. So let us see what we have here. We have plus 2V naught times V and minus 2. So these guys we can cancel out. Also, we have minus 2V naught square plus V naught square. So we can cancel this one and this 2. And this will be equal to V square minus V naught square. So now we have our left side and our right side. We can express now V, instantaneous velocity square, equal to V naught square plus 2A times x minus x naught. So this is the kinematic equation expressed for, like, in terms of velocity and position, except having this time independent parameter in consideration. So that could be helpful. And now let us write down here at the bottom also our kinematic equation x is equal to x naught plus v naught times t plus a times t squared divided by 2. So with these two equations, we, depending on initial conditions, can easily define position of an object in along straight line, assuming that this object is moving with a constant acceleration. So now let us summarize a little bit. We introduced the concepts of instantaneous acceleration and velocity, as for velocity it's first derivative of position over time. For acceleration is first derivative of velocity over time or second derivative of position over time. We considered this case of motion along straight line with constant acceleration, and for this specific case derive the kinematic equation. This is this original kinematic equation, then also which obviously contributes to position of the body. We have initial position, displacement because of initial velocity, displacement because of constant acceleration, and by substituting the independent parameter time in this equation, kinematic equation original, we got expression for instantaneous velocity as a function of position. And of course, you can vice versa determine position as a function of instantaneous velocity. So this is the key information about motion along a straight line. And as I mentioned at the beginning, we do not introduce here any vectors so far, because along a straight line, we don't need to do that. We can only define the sign of displacement, and that will give us the direction of motion, either positive or negative.